Hello again. We're continuing with our study of waves and sound. Now, I asked you to watch this video. It's in the same playlist as this video. But just as a quick reminder of what Hewitt explains, let's go and talk about his explanation for the Doppler effect. So the Doppler effect says that if you have a source of waves, so in the video that you just watched, it would have been a little bug, and he's making waves, and he's just standing still. So the first wave he made was this outer one, because it's the first one because it propagated all the way out to here. Then after that, the bug made this wave. Then after that, the bug made this wave and this wave. Now, if he is moving so that he makes the first wave when he was here, and then the second wave when he was here, and the third one, and so on, then in the direction he's moving, the waves are closer together because he's moved since when he made each one. So a person standing at location B would see the waves coming more frequently. And if this were sound rather than water waves, you'd hear a higher pitch. Or if this was light waves rather than water waves, you'd see a higher frequency of light waves, which would appear blue. So that would be called blue shifted. On the other hand, the observer at A, because these waves are further apart, sees a lower frequency for the waves coming in. If it's sound, it would have a lower pitch. If it were light, it would be relative to, let's say, the starting color green, it would be a longer wavelength or a lower frequency, which would be towards the red. So we call that red shifted. In astronomy, stars that are coming towards us are called blue shifted stars. Stars that are going away from us are called red shifted stars. So the Doppler effect is something that we hear very frequently. Whenever a vehicle goes by, the sound that it makes has a higher pitch when it's coming towards us and a lower pitch when it's going away from us. This is really noticeable when you're watching TV coverage of automobile races. The camera is there watching the cars go by, and when the cars are coming towards you or coming towards the cameraman, you can hear and then when the car passes by and is going away, it goes to so you get this kind of sound. And whenever there's an airplane going by overhead, the sound of the airplane is, and then after it passes by us, it's a lower pitch, like that. So this is something that happens all the time in our everyday life. Let's see. So I'm going to ask you to do homework and quiz problems that involve a little bit of math. And so you're going to need to use these formulas. Notice that there are actually two formulas for the Doppler effect. The first formula talks about the sound that you will hear if you are moving. So we don't take trains very often in Southern California, but if you ever have a chance, let's say you're on the metro and you hear that you're coming to an intersection, and you might hear the warning, to keep the cars from getting on the tracks, going bing, 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 and then when the train passes that, you're going to hear a lower pitch. So you're going to hear bing, 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 a lower pitch. So that's what this is about. So let's take a look at what this says. The F prime means the modified frequency. F without the prime means the original frequency. So this is the thing that's just staying still. It's making a certain frequency sound. The V here is the speed of sound, which is 343 meters per second. And the U is your speed. And so you do this math, and you're going to get the modified pitch. It'll be a higher pitch because this is positive when you are going towards the source, and it'll become a lower pitch, a negative sign, that's what I'm saying here, if you are moving away from the source. The process for a moving source, and then you are standing still listening to the source, let's say coming towards you, is to calculate that. Here you have a formula. Notice that actually these two formulas are going to give almost the same answer as long as the speed is u is quite a bit less than the speed of sound. So let's say that the speed is, let's say, 1% of the speed of sound, then it doesn't really matter much which formula you use. You're going to get almost the same answer. Anyhow, so this describes what you will hear when, let's say, a car passes by you. And so F here is the noise being made, let's say, by the engine of the car, the race car. And F prime, you're listening, you're standing on the ground listening to this car, and this is what you hear. And U is the speed of the car, and V is the speed of sound. And this negative sign, but it's in the denominator, means that you are going to hear a higher pitch. And that's the case where the source is coming towards you. If the source is going away from you, you want to switch the negative sign to a positive sign. Let's do an example. In my backyard, there's a hummingbird that likes to buzz right past me at high speed. When he flaps his wings, I can hear that humming sound at 50 hertz. That's when he's hovering. When he's coming towards me, I'm going to hear a higher pitch. And when he flies, he's fast. He's going 10 meters per second. So let's see what the frequency I'm going to hear is when he's coming towards me. I'm going to use this formula right here, and let's get started on it. So F prime is the frequency that I'm going to hear, and I'm going to multiply this by 1 over 1 minus his speed. U is his speed, 10 meters per second. And I'm dividing that by the speed of sound, 343 meters per second. And that multiplies his original frequency, the humming, at 50 hertz. Now, when you do this on the TI calculators that I recommended you get, the calculator's smart enough to know that division, 10 divided by 343, that's going to come before the 1 minus part of it. So you don't need to put parentheses around this part. But it doesn't know that the denominator needs to be taken care of before doing this division here. So you need to add these parentheses when you're doing the math on your calculator. And then once you've done this, you could press the reciprocal key, press equal and then reciprocal and then multiply by 50. Or you could do it all in one shot by adding parentheses around all of this and then multiplying by 50. Okay, different ways to do it. Anyhow, when you do this, you're going to end up with the stuff in all of this stuff here works out to be 1.03, and that multiplies the 50 hertz, and you get a final answer of 51.5 hertz. So now your turn. I'd like you to go ahead and do the B part of this question. Get your calculator out. Let's see if you can punch in those numbers and without messing up. Okay? The answer is coming next. The next thing we're going to look at is standing waves. But before we move on to that, I want to back up just a bit and show you the answer to the Doppler example. So you should have gotten 48.5 hertz when the hummingbird was going away. And at the end of all of these notes, there's going to be another question, and this will be the answer to that question when we get to it. All right, so moving on, we're going to be talking about standing waves. And so far, we've been looking at, I guess you'd call them normal waves, just waves that go on and on and on. And those are called traveling waves. And then now we're going to look at this other thing called standing waves. Now, to really, the easiest way for me to show you what this is about is to go to the PhET simulation, which is what I'm going to do right here. And I'm going to show you the actual steps to getting to this one because, unfortunately, the University of Colorado has improved this particular simulation, and the new improved one is not as good as the old one. So rather than using this one that they're kind of putting up front, we need to go digging into the past. So here is the original one from way back. It uses the Adobe Flash Player, so that needs to be installed on your computer. And so I'm going to run that. And no, I don't want the new one. I want the old one, the legacy version. And here it is. So let's look at traveling waves first. I'm going to turn, well, let's just show you what happens when I do this. This is a traveling wave, but it's a fixed end. So what I'm going to do is I'm going to switch it to no end. And so now when I do this, the waves travel out the window. I guess there must be a continuation to the right that we don't see. Now it doesn't look like much because you have a lot of damping, a lot of friction. So let's turn the damping down. And now we have traveling waves. I can even make them do this. I oscillate. Okay, so they go out, 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 out. Now, what if the window were closed and we go back to a fixed end? Well, right now there's a bit of chaos happening because there's no friction at all. So let's put a little bit of friction. Now to try to do a better job of explaining what's happening, I'm changing modes here. I'm asking the simulation to make pulses. So let's see what happens. You can see that a pulse comes and reflects, and it's an inverted pulse. Now, what if I were to repeatedly do pulse, 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 pulse? Well, in some places, you're going to get the incoming waves and the reflected waves. They're going to be interfering with each other. And if I make it happen on a continuing basis, the pulses, the waves which are bouncing back and forth, are interfering with themselves. And in some places, you're going to get constructive interference, and in some places, you're going to have destructive interference. Now, in order to make things a little bit more clear, I'm going to reduce this amplitude. Let's make it 5. And let's reduce the damping. Let's maybe make it 2. Okay, so it becomes a little bit more clear what is happening. Places where things are not moving very much have a name. These are called nodes. So you have a node here, a node here, a node here, node, node. The nodes are places where destructive interference is happening. Now, technically, there's also a node here and a node here. And whether or not you're going to count the two end nodes kind of depends on the teacher or the textbook and so on. So I'm going to not count the end nodes. The places where you get constructive interference, where you get a lot of motion, are called the antinodes. So A is going to stand for antinode. We have A, and A right there. The fact that you can fit only a certain number of nodes and antinodes in the space between the two ends of the string is a feature of resonance. And in order to explain this a little better, I'm going to switch to a different frequency. I'm going to go to, let's see, 5. I don't know what the units are, but I know that, okay, here we're going to set this to 8. And let's get rid of what's happening right now. And let's bring the damping way down. And I picked 8 here because I know that at this particular frequency, half of a wave fits in the space here. Right here, between here and here, I can fit half of a wave. So I want to show you what I mean by that. Stop it. All right. If I draw this, you see this thing will keep going, and it's going to go off the screen here, but you can imagine that what I'm doing is I'm drawing this, and this half of a wave fits in here. So we have one antinode here, and I suppose you could say you have a node here and a node here, but for our purposes, it's going to be easiest to count antinodes. So at this frequency 8, I can fit one antinode. Now what if I were to double the frequency, maybe make it 16? Now at 16, I can fit an antinode here and an antinode here, and I wanted to say I can put a node here. Okay. What if I were to go 8 plus 8 again, let's see, so that was 16, plus 8 again. That would take us to 24. Now we have 1, 2, 3 antinodes. So I'm sure you're seeing a pattern by now. The 8 hertz, or 8 whatever these units are, they're not really hertz, is called the fundamental frequency. The 16 hertz is twice the fundamental frequency. It's called the second harmonic. The fundamental frequency, that's new vocabulary, is called the first harmonic. And the 24 hertz would be the third harmonic, and so on and so on. And as you go up in frequency, you have more and more harmonics. Now, I want to show you a feature of standing waves and resonance. Now, I already mentioned to you that waves store energy. Now, one of the interesting features of resonance is that it provides a way to accumulate a tremendous amount of energy. I've tweaked the frequency here. 24 hertz is not exactly on the resonance frequency. 25 happens to be. Now, you can see that to make the string oscillate, it's going up and down just a little bit. Now watch what happens when I bring the damping way down. So one of the features of resonance is that for a little tiny bit of motion to get things going, you get a very large amplitude. So what's going on here is you get energy coming from some energy source here. I mean, this would normally be your hand, or I don't know, maybe the wind making a string blow. But anyway, you're getting a little bit of energy going in, a little bit of power, but as the energy goes in, it's accumulating, it's building up in the string. And so at resonance, you can get this accumulation of energy. Now, what if I were to deliberately ask for the wrong frequency? What if I were to go to, let's say, 28 hertz? Let's see what happens. I'm going to now erase, so to speak, erase this, and we're going to go back down to the same damping of 1. Let's see what happens. You see, it doesn't work. In terms of the discussion of Q that we had before, what's happening is that there is a pattern here. So this is the frequency of this thing that's making it go up and down. And 28 hertz happens to be like somewhere over here. And this is the amplitude of what you're going to get out. And so you're off resonance. This thing right here is called the resonant peak. And the resonant peak happens to be 25 hertz. And then if you're at 28 hertz, it doesn't work. Okay, I think that's pretty cool. Okay, so now that we've gone through all of this demo stuff, let's kind of recap some of the stuff that we learned. The length from one end of the string or the other end to the other end of the string is called the cavity length. Now the word cavity actually refers to musical instruments like flutes. So a flute is hollow, it's a cavity. And you get waves bouncing back and forth between the two ends of the cavity, and so you get resonance. The fact that resonance can only happen at particular frequencies relates to the fact that a flute, will produce a particular frequency, and so that's the basis for musical instruments. It's this idea of resonance and cavity lengths. Now, the whether or not you have resonance depends on certain rules. So one way of looking at the rules is that you will get resonance if the cavity length is equal to half of a wavelength, or equal to 2 halves of a wavelength, or 3 halves, or 4 halves. Now, one way to remember this is that you could have one antinode in there, and that this is half of a wave. You could have 2 antinodes, right? Here's an antinode and another antinode. You could have 3 antinodes, and so on. So to fit an antinode in there, you need to fit a half of a wave in there. Now, doing a little bit of algebra, you can now work out what from this, you can work out what the wavelengths can be. So, for example, L equals lambda over 2 leads you to lambda equals 2L. L equals 2 lambda over 2, that leads you to lambda equals 2L over 2. L equals 3 lambda over 2 leads you to lambda being 2L over 3, and so on. Now, the frequencies are the speed of the wave divided by the wavelength. So now these things lead to the frequencies being V over 2L, or 2V over 2L, or 3V over 2L. Now, this would be the fundamental frequency, also known as the first harmonic. This is the second harmonic. This is the third harmonic. The next thing I want to discuss briefly is resonance with air. Musical instruments based on air, like flutes, trumpets. What we've discussed so far has been resonance in strings, which works for explaining the sound, let's say, of violins. The important thing when we're talking about violins and guitars and so on is that you have nodes where the strings are attached, so you're going to have nodes for sure at the two ends, and depending on which harmonic, you may have one antinode, or you may have two antinodes, or three antinodes. And so when you have that, you're going to have the frequency, or twice that frequency, or three times that frequency. But when it comes to musical instruments or resonance in air cavities, the thing that determines where you have the nodes is the end of the pipe that the resonance is happening in. So here I've got a pipe which is closed at both ends. And so you are going to have an antinode in the center because, well, it's possible for the air to move back and forth, to slosh back and forth. Now, of course, you need some energy source to make this happen. In a musical instrument, it's the musician who blows into whatever, the trumpet or the flute. Here, I'm not really saying how the energy source is getting in. For one thing, this is a terrible instrument because you see this instrument is closed at both ends. So if you actually made this instrument, you wouldn't hear much because the sound is trapped inside. But, just for the sake of explanation, I want to talk about it. So you can have a first harmonic where you have an antinode here, or you could have two antinodes, so an antinode here, and the air would not be moving right here. So this would be a node. Okay, so first harmonic, second harmonic. This is not a good instrument. A better instrument is where you have the two ends of the pipe open. Now, this is a little strange. You see, when you have the pipe closed, the air molecules are trapped, right? They can't get past the end. Whereas with an open pipe, the air molecules can easily go in and out. And in fact, it's so trivially easily that this makes an antinode happen here. So you get an antinode at an open end, another antinode at the open end, and you're going to have a node here. So if you compare, right, compare this one with this one, the roles of nodes and antinodes have been, swapped. The frequency is going to be the same for this one and this one. Remember, the frequency is determined by how many half waves you can put in here. The wavelength for the flute is, let's draw from there. So this is a wave This is lambda. On the other hand, for the saxophone, from here to here, this is a quarter of a wave, another half wave. So for the same length, from here to here, let's say this is 1 meter, a 1 meter long flute, or a 1 meter long saxophone. The saxophone's wavelength is twice as long as the flute's. And so its frequency will be twice as low, and so it'll be twice as deep a sound. So a saxophone of a given size has a deeper sound than a flute of that size. On the other hand, there's some funny things about saxophones. They have a very special sound, a very unique sound, and that's because when you play, you cannot have a second harmonic. You see, there's no way to put two half waves in here. The next harmonic that's possible is the third harmonic. And then there's no fourth harmonic. And then the next one after that that's possible is the fifth harmonic. The last thing that I just want to mention briefly is that lasers work on the idea of waves resonating in a cavity. So the laser cavity consists of two mirrors. So this is a diagram of a laser. So you've got the waves that are trapped between these two mirrors. And the waves, the light waves, bounce back and forth, just like I was showing you with the waves bouncing back and forth on the spring in the simulation. And they do the same process. They're interfering constructively and destructively, and as you saw in the simulation, you're putting in energy, but the energy stays in there and it's accumulating. So you put more and more, the power's going into the cavity and it's building up power. And so you end up with a very intense light in the space between the two mirrors. Finally, to get the laser light to come out, there's either going to be a little tiny hole drilled in the end of this mirror, or the surface here is deliberately not 100% reflective. They may put in a 99% reflective mirror at this end, whereas this end here is 100% reflective. And so that's how the energy, the light that's been bouncing back and forth in here comes out. This is another very interesting thing about resonance effects. The last thing I want to show you here's a little summary of different formulas that we looked at. And here is a practice problem. And remember, the answer to the practice problem is at the beginning of this video. Okay, this has been a big chapter. There's a lot of stuff here. I hope you liked it. Bye-bye.